So here are 3 practice synthesis questions that all involve Diels-Alder reactions. And so the first question is make this from 4 carbons or less, the second question is 4 carbons or less again, and this one is 4 carbons or less and benzene. Now, hopefully if I can figure it out, I'll have annotations here that allow you to click on them and skip to the part of the video where I go over the specific questions. But for now, you can pause the video, try and solve these yourself, or just stick along and we're going to go in order 1, 2, and 3. So the first question, number 1, we need to synthesize that from 4 carbons or less. And whenever you see a 6-member ring, the first thing you should instantly think is Diels-Alder. Because Diels-Alder is your go-to reaction for making 6-membered rings, until we talk about a couple reactions from the third exam. Now, one thing you have to recognize is, well, the Diels-Alder product, what did we say that always involves? It always involves a 6-membered ring with a double bond in it. But here I have a 6-membered ring without a double bond. If you go back to that reaction list from the basics video I posted, one reaction gets rid of carbon-carbon double bonds going forward. And that was the reaction H2PDC. What that does is it takes a structure with a double bond and turns it into a structure with only single bonds. Now, we're talking about carbon bonds. So carbon-carbon double bond becomes carbon-carbon single bond. And I'm free to put that double bond wherever I want it to be. So I have to think, well, it's a 6-member ring. Where do I want to put that carbon-carbon double bond? I have options. I can put it here, I can put it here, I can put it here. Where's the best spot? Well, remember the other thing that every good Diels-Alder reaction needs for synthesis problems. Your dienophile must have a good withdrawing group. And I said before, it's typically a double bond O. Well, we don't have any double bond O in here. We don't even have a withdrawing group. All we have that's special is a methyl sticking off and an OH. OHs aren't withdrawing groups, they're donating groups. But there's a way to turn carbonyl C double bond O into OH going forward. Now, on that cover sheet I gave you in the basics, I only talked about turning double bond O into, I only talked about turning OH into double bond O. And that reaction was PCC. If we want to go in the opposite direction, turn a double bond O into an OH, what you will use is NaBH4, a good reducing agent. So I see that I need this OH to become a carbonyl. And remember, I'm going from a carbonyl to an OH. So I'm going from a carbonyl to an OH. If I'm going in this direction, I need to use NaBH4, not PCC. Pay attention to the direction of the arrows. And so for that, I'm going to draw an arrow, and I'm going to say over that arrow, I'm going to use NaBH4. And so now that OH will just be a double bond O. And so I have double bond O. And now I have everything. So now I know where my double bond between the carbons should be. If this is going to be my withdrawing group, well, my withdrawing group has to be attached to one of the 2 carbons of my dienophile, the carbon-carbon double bond that attaches to the diene when you make the ring. So that means the best spot for that carbon-carbon double bond would probably be here. Because that would mean this is carbon, 1, here's 2 and 3 where the double bond is, 4, 5, and 6. And I'll remember this again, 1, 2, 3, 4, that's enough, 4, 5, and 6. So these 2 carbons on the right side were part of the dienophile before I did the Diels-Alder. So now that I have the double bond and the withdrawing group, I'm ready to actually do the Diels-Alder reaction. What goes over the arrow when you're doing the Diels-Alder reaction is heat. So over this arrow, I'll write heat. And now I have to figure out the 2 pieces that came together to make this. When you're undoing a Diels-Alder Diels-Alder product, what you can do is just start by redrawing the exact same thing you started with. So the 6-member ring, the double bond O, and the carbon-carbon double bond. And if you number it the way I did, where 2 and 3 is where your carbon-carbon double bond is, we know where the bonds we need to make are. The bonds we made are between 1 and 6 because that separates the diene from the dienophile up here, and 4 and 5, which separates the diene from the dienophile down here. So I'm going to erase what we're going to renumber I have 1, 2, 3, 4, 5, and 6. So you're going to erase the bond between 1 and 6, 4 and 5, and now you're just going to put the double bonds where they belong. We know that the dienophile should have a double bond, so you put a double bond between 5 and 6. You know there's no double bond between 2 and 3 in the starting reactant, but there's a double bond between 2 and 1, and 3 and 4. So these are my two pieces that came together to make this ring through the use of heat. Now, we're not quite done yet, because while this structure over here is 4 carbons or less, I can box that and say that is done. This right here is 1, 2, 3, 4, and then a 5th carbon. So since we don't need to care about these carbons anymore, I'm going to say this is carbon 5 over here. I need to get rid of one of those 2 carbons. So now it just becomes, all right, we're going to use that reaction list from our cover sheet, from Orca 1. What kind of a reaction forms a carbon-carbon double bond? An elimination reaction. So over the arrow, I will have going to this OH minus, a good base. And I need to go backwards to something with a single bond. So I'm going to use the double bond down here, because I chose to. It doesn't mean, you could use this double bond, but only use one. I'm going to use the one on the bottom here. And I need to put a bromine, or a good leaving group, on one of these carbons that formerly had the double bond. In this example, it doesn't particularly matter, because if I put the bromine here, well, there's only one spot that has a hydrogen a single bond away. There, so the double bond would always form there. On the other hand, if I put the bromine in the middle, well, again, there's only one good option for a hydrogen to be pulled off. This one over here or this one over here. They're the same because they're both just methyls. I would never pull off this hydrogen because then I'd make the double bond there, and that looks really ugly. 2 double bonds going to the same carbon, you never want to make that happen until you do some rearrangements, but we'll pretend those don't exist. So let's put the bromine in the middle, just because it's easier to work it with it that way. Okay, so all I did was I said, okay, carbons 3 and 4 are where my double bond I want to get rid of. I'm going to choose either 1 and 2 or 3 and 4 as double bond. I chose 3 and 4, but again, you could have done 1 and 2. Doesn't really matter. You'll, in the end, have to do the same things. So I got the OH over here, the bromine over here. The double bond is gone. And now I need to turn that bromine into something that I can cut with. And remember, your goal is to always turn things back into OHs when you're trying to cut carbon chains, because OHs can use that cutting reaction. So what turns an OH into a bromine going forward? PBr3 or HBr. Now there's an important rule you should know about PBr3 that I didn't mention in the basics video. PBr3 does not work on OHs that are on tertiary carbons, meaning like this example. I cannot use PBr3 here because PBr3, if you recall, is an SN2 styled mechanism, which means it's very subjective to steric hindrance. Long story short, all that stuff means is it can't react on OHs that are on carbons with 3 other carbons attached, tertiary carbons. Which means in this example, you have to use HBr to convert the OH to the bromine. Okay, and now it's just a matter of cutting. So all I have to do from here is, let's say I label the carbon with the OH A, and I can cut any carbon that is a single bond away. So here's a B, here's a B, here's a B. I have 3 options of where I could cut, and it doesn't really matter because all I want to do is get rid of one carbon anyway. So I'm going to cut here. So all I'm going to do now is I'm going to redraw this whole thing exactly the same up here. Double bond O, double bond O. Why did I say double bond O? Double bond carbon, 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 OH. Now I said I want to cut this bond between these 2 A and B's. So I'm going to erase that bond. Now remember, the reaction that involves this cut, you have one carbon with a double bond O on it and another carbon with a lithium on it. The carbon with the lithium on it should be the carbon that doesn't have the OH on it, because it's the one without the oxygen. So I draw the lithium in. And the carbon with the OH, I'm going to erase the hydrogen and turn that single bond O into a double bond O. So it was this plus this, which came together with step 2 H plus to make this product here. And with that, I have finished the synthesis because both of these are 2 carbons or less. Number 2, won't take as long, I think, to explain as number 1. But it points out one key important fact, or point. So we have a 6-member ring, and we know usually Diels-Alder makes 6-member rings, but this 6-member ring has 2 double bonds in it. We said Diels-Alder only made double bond rings with 1 double bond, so what's up with this? Well, it's still going to be the product of a Diels-Alder reaction, but there's something special. Whenever you form a 6-membered ring through a Diels-Alder where you have 2 double bonds involved, that is the result of a Diels-Alder where your dienophile was a triple bond. Because when these come together through its arrows, there would still be a double bond left over even if you use one of these bonds to connect these carbons. So this arrow would connect this carbon here, giving up the double bond. This arrow would move this double bond down like this. This arrow moves this double bond to connect these 2 carbons like so. And so you get a 6-member ring with 2 double bonds in it. So we know that there's a triple bond somewhere in the 2 pieces that made this Diels-Alder product, but then comes the question again, well, where's my diene, which carbons were from my diene and which carbons were from my dienophile? Well, that answer is straightforward enough because we have C triple bond N. And if you look at your cover sheet, you see that C triple bond N is a withdrawing group in much the same vein as C double bond O. And for that reason, all we need to worry about is, well, okay, if this is a withdrawing group and it's attached to a double bond, these 2 carbons must have been the triple bond that were part of my dienophile. So I know that this must be 5 and 6. And then by extension, I know this must be 2 and 3 because that's the other double bond. And then I can just number 1, 2, 3, and 4. So now I'm ready to do the heat step and break this ring apart. Heat. And once again, if you have trouble visualizing where your bonds should come from, just redraw the thing you started with. Everything exactly the same. C triple bond N. Now the bonds that we formed, we know will always be connected to 1 and 4, which connects the dienophile's carbons to the diene's carbons, which means the bond that I'm forming here is between 1 and 5. Now notice in the last question I had 1 connected to 6. Again, really the 2 numbers you need to keep consistent in position are 2 and 3. Whether this is 2 and this is 3, it doesn't really matter as long as your double bond that you have in the product is between those 2. But whether I have 4 and 6 connected or 4 and 5 connected, it's just a convention to help keep track of where the carbons are and where they should go. So I form the bond between 4 and 6, so I'm going to erase the bond between 4 and 6. I form the bond between 1 and 5 going forward. Going backward, that means I'm erasing those 2 bonds, or erasing that bond. Okay? And now I have to put the double bonds in the right spot. In the reactants of a Diels-Alder, the double bonds will be between 1 and 2, 3 and 4, and then the dienophile gets 1 more bond. If this was a single bond, it would become the double bond that we usually expect. But because it was a double bond starting out, it is now a triple bond, and so we have that. And now, even though I have C triple bond N here, well, this thing right here is already 1, 2, 3 carbons, so it's 4 carbons or less, we're done with that. I can just box it and say, okay, this is done. I just have to work on this, because this structure is 1, 2, 3, 4, 5 carbons long. And so it's another chance to get practice at what we did for the first question. So what kind of a reaction ends with a double bond? An elimination reaction. So I'll use OH minus. I'll choose one of these 2 double bonds arbitrarily. Let's use the double bond between 4 and 5 again. And so I have 1, 2, 3, 4. And I'm going to put the Br on the end over here. Okay? Now I need a reaction that adds bromine. I can use PBr3 this time because it's a primary bromine rather than a tertiary, so this will work. And now I go back to an OH. And now I'm at the point where I can start cutting again. So you look at your carbon that the OH is attached to, you label that A. You look at any carbons that are a single bond away, well there's only 1 in this case, and you label that B. And so you're going to be cutting the bond between A and B. And so now you have, what you can do again is redraw what you started with. OH. Now we said the bond that we're going to erase, here's A, here's B. The bond that you are going to erase is the bond between A and B, so I'm going to break that bond. The carbon with the OH, so the carbon A, will now be connected to a double bond O. So I have C double bond O, and then there are 2 hydrogens on that carbon, so that's formaldehyde, but I don't think you really have to worry about that. Point being, that's what you get. And then carbon B, the carbon that didn't have the OH, just gets a lithium tacked on. And so these would be the two pieces that came together to form this. Just don't forget to write over the arrow, step 2H plus. It's okay if these two are on the left side or on the reactant side of the arrow together. Or you could write step 1 with one of these individual pieces over the arrow, either is acceptable. But that's how you go about doing number 2 synthesis. On to number 3, which is meant to be the challenge of these questions, mostly because it combines the first synthesis of the exam 1, the benzene addition syntheses, with the Diels-Alder syntheses. So this question says, make this from benzene or 4 carbons or less. So somehow we need to get this carbon chain attached here to this benzene, and right here we have a 6-member ring. That's probably our Diels-Alder product. So let's approach it from the Diels-Alder side of things first. I want to make this 6-membered ring. So does the 6-member ring have everything I need on it to allow me to do the Diels-Alder? Well, it is a 6-member ring, good. It's a 6-member ring with a double bond, better. But it doesn't have a strong withdrawing group on it. So I'm not ready to do Diels-Alder yet. I need the 6-member ring, the double bond in that 6-member ring, and a withdrawing group. But there's no withdrawing group. All I see is carbons. Now here's the trick of this question. If I wanted a withdrawing group, where would it have to be? It would either have to be off of this carbon, so like a double bond O there, or it would have to be off of this carbon, a double bond O here. But one of those two spots is a lot easier to get a double bond O onto than the other, namely this carbon right here. Because notice what it's a single bond away from, a benzene. And we know a reaction that gets rid of double bond O's that are a single bond away from benzene. The zinc-mercury reaction, ZnHgHCl, will, going backwards, put the carbonyl right back on there. So that should be your first step. And so I will have double bond O here, 6-member ring here, and a double bond here, and a methyl, and then benzene. Okay? And now I can do the Diels-Alder because I have a 6-member ring with a double bond with a good withdrawing group on it. So once more, we're going to do our numbering scheme first of all. So double bond will always be between 2 and 3, so here's 1 and 4, and we'll say here's 5 and 6. So we know we're going to be breaking the bonds between 5 and 4, 6 and 1. So the benzene is still the same. Benzene's bond to this double bond O is the same. This carbon is connected to 6, which was connected to 5. 1, 2, 3, and then 4. Well, we said we're erasing the bond between 1 and 6, so this bond is gone. We're erasing the bond between 5 and 4, so this bond is gone. And now I just have to put my double bonds in the right spot. There should be a double bond between 6 and 5. There should be a double bond between 3 and 4. And there should be a double bond between 1 and 2, so I have this. And then there's a methyl over here that I forgot to draw. So now I have my two pieces. This plus this, with heat over the arrow, will give me this product of a Diels-Alder reaction. Now, because both of these structures, this structure is not 4 carbons or less, and this structure is not 4 carbons or less or benzene, I have to draw arrows for both of them. So let's look at these pieces individually, and if you ever have to do this on your exam, you would just have to draw the 2 individual synthesis steps separately. It's okay if you draw one and then on a separate step down below in the answer space, draw the other one. Because as long as you justify how you make each piece, you're good. It doesn't have to like directly point to it. So let's do this piece over here first. Well, we already worked with this one in the first question. When you see 5 carbons and you have, well, when you see you need to cut carbons and you have carbon-carbon double bond, use OH minus to do an elimination reaction. And so we have, let's use the double bond on top this time. I'll put a bromine on the end over there, because remember going backwards, going forward, what this does is it pulls off a proton, forms a double bond by kicking the bromine out. So the proton it pulled off must be over here, because those are the 2 bookends of your double bond. And then I can do a reaction that replaces OH with bromine, because remember your goal is to always get an OH there, so I'll use PBr3 again, because it's not a tertiary carbon, I can replace that bromine easily. Now I have the OH in a spot where, well now I have an OH, and so I can cut with it. So I have this, double bond over there, that. I keep saying double bond over for some reason. Okay, and so how do I cut this? Label your carbon with the OH A, label any carbons a single bond away from A, B, so there's only one B in this case. You're going to break the bond between A and B. So that means, over my arrow I always have step 2H plus, redraw what I started with, OH carbon, carbon, double bond, methyl. And I said I'm breaking the bond between A and B, so I erase that bond. Carbon B, the carbon that didn't have the OH, gets a lithium. And then the carbon that had the OH, carbon A, gets a double bond O. And so I have this plus this with step 2H plus will yield this. And so this is one piece done now. I have two pieces that are 4 carbons or less, so that's good. But I still have to show how I made this from benzene. So draw your arrow to this. How do we add a carbon chain with a double bond O on it? Well, that's just the carbon chain with the double bond O and a Cl, where that bond to the benzene is. So that double bond, and then AlCl3. And that will give me the benzene that I need to make. And so now I have all my pieces 4 carbons or less and starting from benzene. So that's how you go about this synthesis problem.